This tutorial covers the third part of the block 1 of the T325 course. It is about error control coding. As an outline of this tutorial, we're going to start with an introduction. Then we will have some overview of error control coding where we're going to present some concepts. Then we will move on to talk about block code, in particular the rectangular and Hamming codes. We then move to talk about interleaving process used with the error control codes, and finally the tutorial ends with some talk about the low density parity check and Reed-Solomon codes. So let's have first some overview about error control coding, and we're going to start to explain some of the concepts that we are going to use in the rest of this presentation. So the first concept we're going to address is the bit error ratio, or BER. By definition, it is a measure of how badly a signal is affected by errors, and as its name indicates, it's a ratio of the bits that are in error over the total number of bits to be transmitted. So if I ask the question, which is better, a high bit error ratio or a low bit error ratio? So of course a lower bit error ratio is better, since lower BER means that the number of bits to be in error during the transmission is lower, which is better for the transmission. And another example, if we have 10 errors in 10,000 bits, what is the bit error ratio? So as we said, it is a ratio of the number of bits in error over the total number of bits. So the bit error ratio is 10 over 10,000, and thus it is 0.1% of BER. So let's move to the positioning of coding and decoding in the overall transmission process. So if we look at the schema here, we're going to see a block representation of any transmission between a data source and a data sink. So the data source transmits a message, is emitted from the data source. The transmitter converts each message to a code word that that will be sent through the channel to the receiver, that will receive the code word and then converts it back to a message that will be sent to the data sink. So the data source sends a message to the data sink. This is the first point. The transmitter do the conversion between the message to a code word suitable to be sent through the channel. So this is the process that we call encoding. And the receiver converts back the code word to a message, and this is what we call decoding. So what is a code? A code is the set of rules that determine how can we get from any given message a certain code word. So the transformation of the message into a code word is called a code. So usually codes are accompanied with adding some additional information to the message. This is why the term redundancy is used. By definition, the redundancy is a measure of the proportion of code that is extra beyond what is needed to convey the message. So we have the message, we will add some extra bits. So this extra bits is called the redundancy. So usually when we represent a code, we say that we have a code that transforms a message of k bits into a code word of n bits. This is why this code is represented by the nk representation. As I said, n is the number of bits in the code word and k is the number of bits in the message. Sometimes the nk is used but in bytes instead of bits. So these extra bits that we added are called redundant bits. So we see that we have the message, we have these extra bits, and to get the code words. So in general, n is greater than k. So the code rate is the amount of message bits in the code word, and this is represented by k over n. The redundancy rate is the amount, or the ratio, is the ratio of the additional bit over the total number of bits in the code word. So if I had k bits and I get n bits, the number of bits that I added is n minus k, and thus the redundancy rate is n minus k over n, which is the total number. So one of the questions that we need to address is what do you think is better? Is it better to compress than code or code than compress? Just to say that compression is something that is very common in the transmission in order to reduce the size of any information or data to be sent through the transmission channel or for the storage even. So now I have two techniques that will be used, which are the compression and the coding. To simplify the answer, I will add some hint, which is that compression removes the redundancy from the message to be compressed, and coding adds redundancy, as we said before, to the message to be coded. So I have two mechanisms, one that remove or reduce the redundancy, and the second one that adds the redundancy. So the question is, which is better? So let us think. If I consider the code then compress, so the coding will add some bits and then the compression will remove the redundancy. So these additional bits that serves to detect or to correct the error, if I'm talking about the error control code, or in general the purpose of the code itself, will be removed during the compression. So if I transmit the results of the code then compressed process, I will get a message where the redundant bit from the code are removed or reduced, and thus the utility of the code will not be there. While if I compress then code, so the compression will reduce the redundancy that exists in the message, but then the code will add the util bits that will serve the coding purpose, which is in our case the error control code. So compressing then code is better than code then compress. So another concept that we're gonna see is the code distance. The code distance, which is sometimes called as Hamming distance after Richard Hamming, the scientist that defined this value, is by definition the minimum number of places in which any two code words differ. So if I want to see the minimum difference between any two code words, this is defined by the Hamming distance. So how to determine the Hamming distance? In order to determine the Hamming distance, and as I said before, it is the minimum number of places separating two different code words. So I have to check all possible pairs of code words, and for each pair I will check the differences between these two code words. Let's take an example. So let's consider this code where the code table states for the message, for each message, the corresponding code word. So the message 00 has the code word 00001, 01 has this code word, 10 has another code words, and 11 has this code word. So if I want to measure the Hamming distance, I need to address all possible pairs of code word, and this is in a kind of matrix, and then consider every two code word and find the number of places separating these two code words. So let's consider this. I'm doing this matrix where I'm writing the different code words in the column and in the line, and then I will compare each pair. So I will compare the 00001 with the rest of code words. Of course, if I'm comparing it with itself, the difference will be 0, and this explains the 0 in the diagonal. So let's consider these two code words. How to measure the differences? I'm considering the first bit in this code word and the first bit in this code word. These are the same. Both are 0. So there is no difference in the first bit. The second bit is 1 and this one is 0. So this is one difference. Here I have 0 and 0. So far I have only one difference. I have 1 and 0. So this is a second difference. And I have 0 and 1. So I have 3 differences. The same applies for this code pair of code words. While if I'm comparing these two code words 10100 and 01010, I will notice that I have 4 differences in the first bit, in the second bit, in the third bit, in the fourth bit, but the fifth bit is the same, so I have 4 differences. After completing the lower part, I don't have to fill all the matrix since it will be symmetric, so these value will be the same, this value will be the same as that, so I'm just filling the lower part of the matrix. And returning to the definition of the Hamming distance, it is the minimum number of places separating any 2 code words. So the minimal value of these numbers is 3, which is the Hamming distance of this code. So in practice, what is the meaning of the Hamming distance? Let us consider the following example. So I'm considering this schema where the circles that are in red represents correct code word, and these are the number of places separating, which means the white circles are error or incorrect code word. So if I have 3 differences between, or 3 places separating any 2 code words, this means that between these 2 code words I can find 2 incorrect code words. So let's suppose that I want to send this code word, and during the transmission I have 1 bit in error. This 1 bit error will move this code word to this incorrect code word. At the reception, the receiver will receive this value. So it will check the list of code words that are available similarly to this table. So it will check if the received value is among the existing code words. So since it is incorrect, it will not figure in the list of the table of code words. So what the receiver will do is to find the nearest code word to this value, and the nearest code word to this value is this code word. So while first it will detect that there is an error because the received value is not among the list of code words, and second, it will correct the error by changing this received value to the nearest value of correct code word. So it will correct it to this value, and thus the sent and received code word will be the same, and thus the error is corrected normally. Suppose that there are 2 bits error during the transmission. So this value will be moved to this value. The first error will move it here, and the second error will move it here. So the receiver will receive the value in 1. While receiving, first it will try to check if there is an error. Since this value is not among the correct code words, so the receiver will detect that the received code word is incorrect. So we can detect the error. Second, it will try to correct, and as we said before, when we try to correct, we will find or correct to the nearest correct value. And if I'm comparing, the distance from the received value to this value is 2, while the distance to this value is 1. So the nearest value is that value. The sender sends this value, and the receiver will correct to this value. So the receiver failed to correct the received code word. So as we saw, the receiver can detect the error, but it will not correct the error appropriately. So this leads us to the definition of the property of the code, taking into consideration the Hamming distance. If a code has a Hamming distance of d or n, it can detect d-1 errors. So let's consider this example. We have a Hamming distance of 3. So if I have 1 error, I can detect it. If I have 2 errors, I can detect it. But if I have 3 errors, the sent code word will arrive at this value, and the receiver will find that this value is correct, so it will not detect the error. So for n-1, which is 2 in this case, I can, or d-1, I can detect the error. In the correction, the formula is a little bit more complex, because when the distance is 3, if I have 1 error, I can detect it and correct it, since I will be correcting to this value. If I have 2 errors, so I'm crossing the half position or the middle position. So the correction will be not appropriate since the value received will be corrected to this value. So the formula is as follows. I have to make sure that the number of errors is less than half of the distance. So this is done through this formula. If the Hamming distance is n and n is odd, the code can correct n minus 1 over 2. If n is even, it can correct n over 2 minus 1 in order to avoid fractions and non-integer numbers in the value. So in our case, if n is 3 or d, we can use the 2 terminology, but usually we use the d to avoid to differentiate it with the nk representation. So let's consider d. If the Hamming distance d is 3, 3 is odd, so I can correct d minus 1 over 2, 3 minus 1, 2 over 2, 1, which is the case of 1. If it is 5, it is 5 minus 1, 4 over 2, so I can correct 2 errors. If it is 6, I apply the second formula, 6 over 2, which is 3 minus 1, so it is 2 errors. So if I want to classify the error control coding, we can classify them into 2 parts: detection, error detection codes and error correction code. The first part we're going to address is the error detection. The basic error detection mechanism is the parity check. The parity check is a very simple method to detect single errors. So I can detect only 1-bit error. However, even though it is simple and the number of errors is very limited, which is 1-bit error, which is not commonplace, the parity check is a fundamental part of a more advanced code, and one of the examples we're going to see is the Hamming code that we're going to address later on. So the parity check is done either on odd parity or even parity check, and most commonly we are using the even parity. How to do or how it works? So if I'm using even parity, I have a message of n bits. Let's say I have 6 bits. I count the number of ones. If the number of ones is even, the parity check bit that I will add will be 0 in order to keep the total number of ones even. If the number of ones in the message is odd and I'm using an even parity check, I will add a parity check bit that is set to 1. So if I have an odd number of ones, am I adding one extra 1 bit set to 1? So the total number will be even. So simply, in few words, the parity check makes sure that the number of ones is either even in case of even parity check in the code word, or odd in the odd parity check in the final code word. So another error detection code is the cyclic redundancy check that we are not going to cover in details in this part. It is more powerful. It adds 1 or more bytes. So we're going to see, usually we use the term CRC for cyclic redundancy check. If you do a quick search, you will find that we have CRC 16 by adding 16 bits, or CRC 32 by adding 32 bits, which is 4 bytes. It is more flexible than the parity check we have seen, since it detects many different combinations of error. So the question is, what do I do, or how to correct the errors when I detect it? A very basic mechanism is that if I detect an error, I ask for a replacement of the data that is erroneous. So the problem is that first we're going to have some delays, since the receiver has to wait until the sender receives the request to send the data again, and then to send it again. So this might not be acceptable in certain type of applications, especially real-time application. And another thing is sometimes the data are sent on the fly, so the correct data might not be available to be resent at the sender side. So the second category of actions to be done when the error is detected is what we call the forward error correction, which is defined to overcome the limitation of the ARQ, the automatic repeat request, and it is done by adding extra bits that will help the receiver to correct a certain number of errors, and this is what we are going to see in the next part. So the error correction code that are more useful than error detection code, since they can actually correct the errors. So the ability to correct these errors would require the use of more redundancy compared to error detection code, since the bits that I will use in the error control will serve both the detection and at the same time the correction. So we can break them into two parts, the block codes and the convolutional code, and each category of code will be further divided in subcategories. So we're going to start first with the convolutional codes. So the convolutional code encodes blocks of input bits as blocks of output bits. It is an encoder that has a memory, so some or certain number of previous bits will be stored within the encoder. And the term convolutional came from the fact that the encoding process can be viewed as convolving, which means combining the message stream with the response of the code. So we're going to see a typical example of convolutional encoder. So usually the encoding is straightforward. The decoding is a little bit more complex. One of the most popular technique is the Viterbi algorithm, and in this mechanism the decoder takes account of what has gone before and what comes after when we decode the current data, and this is why that there is some delay that is introduced. So in order to simplify the concept of convolutional code, we're going to see a very basic convolutional encoder as part of the activity we're going to see next. So as we said, the convolutional encoder has memory. So there is a storage element in the convolutional encoder. In the example we're going to see now, we have a convolutional encoder that is very simple, very basic, with one storage element and one XOR gate. And you know well that the XOR gates, it takes two input and provides one output. If the two input bits are the same, the output will be 0. If they are different, so the output will be 1. So let's consider this example, and where the input sequence is 1 1 0 1. So we're going to start with 1, and then the next bit will be 1, then 0, then 1, and the storage element is initialized to 0. So as we said, we have the sequence 1 1 0 1. The storage element is initialized to 0. So the signal, which is the first bit, will come to this connection point, and in this connection point the signal will be regenerated, to simplify things, and the 1 will arrive to this connection and to this connection. So, and the same process will be done with the 1 coming to this connection. So now let's see how the storage element works. Now the storage element is initialized to 0. At the clock signal, the 1 arrives, and it will, between bracket, push the 0 value that is inside the storage element. So it will move to the output of the storage element, and thus will go to the input of the XOR gate, and the 1 will be stored in the storage element. Now, as we said in the XOR gate, if the inputs are different, 1 and 0, the output will be 1, and the 1 will be stored in the storage element. So for the first bits, the 1 input gives us 1 1 as an output. So in the second input bit, the storage element now has the value 1, and now we're going to see the difference that regarding the output, since the state of the encoder is different than the previous state. So the same will be repeated. The 1 will move to the first input of the XOR gate, and the second one will arrive to the encoder, and the same one, the signal, will arrive to the encoder, or duplicated, and then it will be duplicated to this output. So the one will be stored in the storage element, and the one that exists before will go to the input of the XOR gate. So now XORing these two values will give us a 0 as output, and the 1 will be stored in the storage element, and the output now is 0, 1. And now we can have an idea about the role of the memory of the convolutional encoder. Since in the first case we had 0 in the storage element, and the input was 1, and we got 1, 1. Now when the storage element has the value 1 and the input is the same, which is 1, so we had different output. So for the same input, which was the bit 1, we had two different outputs, which are 1, 1 in the first case and 0, 1 in the second case. So we're going to repeat. So again, the 0 will be moved to the input of the XOR gate, and it will arrive to the storage element and go to the output, the second output. And now the 1 will move to the input of the gate. The output now is 1, 0 XOR 1 is 1, and the 0 will be stored. And finally, we're going to see that the output will be again 1, 1. So the output will be 1, 1, 0, 1, and then the rest of bits. So as an exercise, you can practice this activity. And this activity, which is a little bit more complex, we have 3 shift registers, 3 storage element, and 2 XOR gate, and 3 output bits. But the same principle will be used. When I have one that arrives here, it will go to this storage element and to this output gate, and the output the same will be done. So please do this activity in order to practice the use of convolutional code. This is the raw representation of a convolutional code that shows the internal architecture of this coders or encoder. There are simpler ways to represent the convolutional code, which is the tree representation. The tree representation is a very simple way to represent the output of the convolutional encoders based on the input bit. So let's consider an example. If I want to take the output of, let's say, a sequence of 1, 1, 0, 0, I start at this point. If the input bit is 0, I go to the upper path, and if the input bit is 1, I go to the lower path. So the example I consider is 1, 1, 0, 0. So when I say 1, so I go to the lower path. So the first output will be 1, 1. 1, I go to the lower path, 0, 1. Then 0, I will go to the upper path, and then 0, I will go to the upper path. If I follow the path, the output will be 1, 1, 0, 1, 1, 0, 0, 0. So the outputs are read directly from the tree representation. The problem with the tree is that it grows exponentially, or to the powers of 2. So with the first bit I have 2 choices, the second I will have 4, then 8, then 16, then 32, so 2 to the power n, where n is the number of input bits. Another way to represent the convolutional code in a more compact way is the use of trellis representation. So when we use the trellis, usually we rely to the number of levels of the trellis, which is the number of states in the encoder. And the state of the encoder represents the different possible values or combination of values of the shift register. So I will go back just for 1 second regarding this encoder. So this encoder, the storage element can either have a value of 0 or 1. So the encoder can have only 2 states, which are 0 or 1. So I will have a trellis representation with 2 states. If I consider this encoder, the possible value will be 0, 0, 0, 0, 0, 1, 0, 1, 0. So I have 3 bits that are independent, 3 storage elements that are independent. So given that they are independent, they might take 2 to the power 3 possible value, and thus the trellis will have 2 to the power 3 levels. In some cases, maybe the storage element, if they are mounted in parallel and they receive the same input, they might take the same value, and thus the encoder might not take all the possibilities, and thus let's say I might have an encoder with a 3 storage element, but that has only 4 levels, or even if they are parallel, it might have only 2 levels. So consider that the case is a 3 storage element connected to the same input. So either there will be 0, 0, 0 or 1, 1, 1, and in this case there are only 2 levels of the encoder, 2 states of the encoder and 2 levels of the Trellis representation. So in the Trellis representation, this is an example where we have 2 states, 0 and 1. So if the input is 0i, the states is 0, and we will keep in the state 0. If I am in the state 0 and the input bit is 1, the encoder will move to the state 1. And if I am in the state 1 and I receive a bit 0 as input, the encoder will move to the state 0. And if I'm in the state 1 and the input is 1, I will keep in the state 1. So let's consider an example. Let's say 1, 0, 1, 0. I started here. The input bit is 1. I go to the state 1. Then 0, I will go to the state 0. Then 1, I will go to the state 1. And then 0, I will go to the state 0. In this path, I will read the values. So in this path, I will take 1, 1. Then 1, 0. Then 1, 1. And then 1, 0. And thus the output will be 1, 1, 1, 0, 1, 1, 1, 0. So the example we're going to see now, just for your information and for further reading, is about the turbo codes. The turbo code promised to achieve the ultimate limits of capacity of a communication channel that is defined by the Shannon equation. So this turbo code has a nice story that is nice to read. You can read how the inventors of this code faced the problem of recognition at the beginning, since no one believed that we can achieve the ultimate limits of the capacity. So I advise you to go and read further about this story. And this is used in a wide range of application, mainly in wireless communication, ranging from 3G mobile system to deep space exploration. The maximum theoretical capacity is defined by Claude Shannon's formula, which is C equal B log base 2 of 1 plus S over N. C is the data rate in bits per second, which is also known as the channel capacity. B is the channel bandwidth in hertz. Log 2, of course, you know the logarithm. And the S over N is the signal to noise ratio. So given that the characteristic of log 2, a greater signal over noise ratio will have a greater capacity. A greater bandwidth will have a greater capacity of the channel.